Tonight, we embark on a journey into one of the most profound mysteries in all of physics. We're going to explore a particle so elusive, so extraordinarily difficult to detect, that despite decades of searching, no human has ever directly observed one. Yet this hypothetical entity may constitute the majority of all matter in the cosmos, shaping the very fabric of galaxies, determining the architecture of the universe itself, and solving one of the deepest puzzles in particle physics. We're going to explore the Axion. Before we begin, if you enjoy these deep explorations of the cosmos and the mysteries that lie at the frontier of human knowledge, please consider leaving a like or subscribing to the channel. Your support helps bring these journeys to more curious minds. Now let us venture together into the invisible realm of Axion physics. Look up at the night sky on a clear evening, far from the lights of civilization. You'll see perhaps a few thousand stars scattered across the darkness, pinpricks of light from distant suns. Behind them, if you know where to look, you might glimpse the faint smudge of the Andromeda Galaxy, our nearest large galactic neighbor. The universe seems full of light, full of matter, full of substance. Yet what you're seeing represents only a tiny fraction of what actually exists. The visible matter in our universe, all the stars and planets and galaxies, all the gas clouds and dust, all the atoms that make up everything we can touch and see and measure directly, constitutes roughly 5% of the total mass energy content of the cosmos. Just 5%. The remaining 95% consists of two mysterious components that physicists have labeled dark energy and dark matter. Dark energy, comprising about 68% of the universe, drives the accelerating expansion of space itself, but it's dark matter, making up approximately 27% of the universe, that concerns us tonight. Dark matter doesn't emit light. It doesn't absorb light. It doesn't scatter light. It passes through ordinary matter like a ghost walking through walls. The only way we know it exists is through its gravitational influence on the things we can see, and that influence is profound. In the 1930s, astronomer Fritz Zwicky studied the Coma Cluster, a massive congregation of galaxies about 300 million light-years from Earth. He measured the velocities of individual galaxies within the cluster and found something deeply troubling. The galaxies were moving far too fast. Based on the visible mass of the cluster, the galaxies should have been flung apart long ago, scattered into the void by their own motion. Something invisible was holding them together. Zwicky called this unseen substance dark matter, or in his native German, Dunkelmaterie. Decades later, astronomer Vera Rubin provided even more compelling evidence. She studied the rotation curves of spiral galaxies, measuring how fast stars orbit at various distances from the galactic center. According to Newton's laws and Kepler's insights, stars farther from the center should orbit more slowly than stars closer in, just as the outer planets in our solar system orbit more slowly than the inner ones. But Rubin found something astonishing. The stars in the outer regions of galaxies were orbiting just as fast as stars near the center. The rotation curves were flat, not declining as expected. The only explanation was that these galaxies were embedded in vast halos of invisible matter, halos that extended far beyond the visible stars and contained many times more mass than the stars themselves. Since those pioneering observations, evidence for dark matter has accumulated from countless sources. the cosmic microwave background radiation, that faint echo of the Big Bang, bears subtle imprints that can only be explained if dark matter existed in the early universe. The way light bends around massive galaxy clusters, a phenomenon called gravitational lensing, reveals the presence of matter we cannot see directly. The formation of large-scale cosmic structure, the way galaxies and galaxy clusters are distributed throughout space, matches theoretical predictions only if dark matter provided the gravitational scaffolding around which ordinary matter could collect and condense. We know dark matter exists. We can measure its effects with exquisite precision. But what is it? What is this invisible substance that outweighs ordinary matter by a factor of roughly 5 to 1? For decades, the leading candidate was a class of particles called WIMPs, weakly interacting massive particles. These hypothetical heavy particles, with masses perhaps 100 times that of a proton, would interact with ordinary matter only through gravity and the weak nuclear force. Enormous detectors were built deep underground to search for WIMPs, tanks of liquid xenon and germanium crystals cooled to near absolute zero, waiting for the rare collision between a passing dark matter particle and an atomic nucleus. But the WIMPs never appeared. Despite decades of increasingly sensitive searches, despite detectors that could register the impact of a single particle, no convincing WIMP detection has ever been confirmed. The parameter space where WIMPs were expected to lurk has been systematically eliminated, experiment after experiment pushing the boundaries of sensitivity while finding nothing. In the absence of WIMP discoveries, attention has increasingly turned to another candidate, one that emerges from an entirely different problem in physics, one that was proposed long before anyone considered its potential role in dark matter. That candidate is the Axion. The Axion story begins not with cosmology, but with particle physics, specifically with a puzzle so subtle that it took the most brilliant theoretical physicists years to even recognize it existed. To understand the Axion, we must first understand the problem it was invented to solve, a problem known as the strong CP problem. The strong CP problem, a puzzle hidden in nature's symmetries. The universe operates according to certain fundamental symmetries. These symmetries are not mere aesthetic preferences, but deep mathematical structures that constrain the laws of physics and determine what is and is not possible in nature. Among these symmetries, 3 hold particular importance for particle physics. The first is called charge conjugation, typically denoted by the letter C. This symmetry relates particles to their antiparticles. If you replace every particle in a physical system with its antiparticle, does the system behave the same way? For many processes, the answer is yes, and we say that C symmetry is preserved. The second is parity, denoted P. This symmetry asks, what happens if you reflect a physical system in a mirror, essentially reversing all spatial directions? Does the mirror image system follow the same laws of physics as the original? Again, for many processes, the answer is yes. The third is time reversal, denoted T. This symmetry asks whether physical laws work the same way if you run time backward. If you filmed a process and played the film in reverse, would the reversed process also obey the laws of physics? For a long time, physicists believed all 3 symmetries were fundamental, that nature treated particles and antiparticles identically, that physics looked the same in a mirror. and that the laws governing time worked equally well forward and backward. Then, in 1956, physicists Tsung-Dao Lee and Chen-Ning Yang proposed that parity might be violated in weak interactions, the force responsible for radioactive decay. Within a year, experimentalist Qian-Xiong Wu confirmed this violation in a brilliant experiment involving the beta decay of cobalt-60 atoms. The violation of parity was shocking, but perhaps the universe preserved the combined symmetry CP, treating a mirror-reflected antiparticle, the same as the original particle. This hope was dashed in 1964 when James Cronin and Val Fitch discovered CP violation in the decay of neutral kaon particles, a discovery that earned them the Nobel Prize in Physics in 1980. CP violation has profound implications for the universe. It's one of the conditions necessary to explain why the cosmos contains matter, but essentially no antimatter. Without CP violation, the Big Bang would have produced equal amounts of matter and antimatter, which would have annihilated each other, leaving nothing but radiation. The existence of galaxies, stars, planets, and you and me depends on this subtle asymmetry between particles and antiparticles. Here's where the puzzle deepens. The weak nuclear force violates CP symmetry. We've measured this violation precisely, but the strong nuclear force, the force that binds quarks together into protons and neutrons and holds atomic nuclei together, seems to preserve CP symmetry almost perfectly. This is the strong CP problem. The strong force is described by a theory called quantum chromodynamics, or QCD. Just as quantum electrodynamics describes how electrically charged particles interact through the electromagnetic force, QCD describes how quarks interact through the strong force, mediated by particles called gluons. Quarks carry a property called color charge, which comes in 3 varieties, whimsically named red, green, and blue. The theory of QCD has been spectacularly successful, explaining everything from the masses of protons and neutrons to the behavior of matter in particle accelerators and the cores of neutron stars. But QCD contains a subtlety, a hidden parameter that physicists call theta. This theta parameter, often written with a bar as theta bar to distinguish it from other quantities, appears in the mathematical description of the QCD vacuum, the lowest energy state of the strong force field. Theta can take any value between 0 and 2 pi, like an angle in a circle. And here's the crucial point. If theta is anything other than 0, or very close to 0, the strong force would violate CP symmetry. How would we know if theta is non-zero? One consequence would be that the neutron, the electrically neutral particle, found in atomic nuclei, would have an electric dipole moment. Imagine the neutron as a tiny sphere. If its positive and negative charges were perfectly centered, the neutron would have no electric dipole moment, no preferred direction regarding electric fields. But if theta is non-zero, the internal structure of the neutron would be slightly distorted, with positive charge shifted slightly in one direction and negative charge shifted in the other. This would create a tiny but measurable electric dipole moment. Experimentalists have searched for the neutron electric dipole moment with exquisite precision. The current best measurements, conducted by collaborations using ultra-cold neutrons and extraordinarily sensitive magnetometers, have found no dipole moment down to incredibly small values. The upper limit on the neutron electric dipole moment is less than roughly 1.8 times 10 to the negative 26 electron charge centimeters, based on measurements published in 2020 by the NEDM collaboration at the Paul Scherrer Institute. This is an almost inconceivably small number, corresponding to a charge separation of less than a billionth of a billionth of a billionth of a centimeter. This null result tells us something remarkable about theta. Based on the theoretical relationship between theta and the neutron electric dipole moment, the experimental constraints imply that theta must be smaller than about 10 to the negative 10. That's 0.001 out of a range of possible values from 0 to roughly 6. Theta appears to be essentially 0 to 10 decimal places. Why should this be? There's no known reason why theta should be 0. In the standard model of particle physics, theta is simply a free parameter, a number that must be measured rather than calculated. It could be any value, and the universe would still function according to the same physical laws. But for some reason, nature has chosen theta to be almost exactly 0. This is the strong CP problem. Why does the strong force conserve CP symmetry when nothing in our fundamental theories requires it to do so? It's called a fine-tuning problem because it seems as if nature has carefully tuned the value of theta to be nearly 0 without any apparent reason. The problem has been described by some physicists as the most underrated puzzle in all of physics. Unlike the cosmological constant problem or the hierarchy problem, which receive enormous attention, the strong CP problem lurks in the shadows, less discussed but no less profound. It asks why nature seems to have chosen one specific value, 0, from a continuous range of possibilities, with no apparent mechanism to enforce that choice. Consider the strangeness of the situation. The weak force violates CP symmetry. We've measured this violation with exquisite precision in the decays of kaons and bemesons. The violation is small but real, arising from a complex phase in the quark mixing matrix. This violation has profound implications. Without it, the Big Bang would have produced equal amounts of matter and antimatter, annihilating to leave nothing but radiation. Our very existence depends on CP violation. Yet the strong force operating at similar energy scales and involving the same quarks shows no CP violation at all, down to incredibly stringent limits. It's as if two aspects of nature, both involving quarks, both capable of violating CP symmetry, have made radically different choices. One embraces CP violation, the other rejects it utterly. The mathematics of QCD makes this dichotomy even stranger. The theta term that would produce CP violation isn't added artificially. It emerges naturally from the structure of the theory. The QCD vacuum isn't simple emptiness, but a complex superposition of topologically distinct states, characterized by an integer called the winding number. Quantum tunneling between these states, mediated by instantons, generates the theta term as naturally as any other aspect of the theory. Gerard et Hooft's pioneering work on instantons in the mid-1970s revealed this vacuum structure, simultaneously solving the U1 axial anomaly problem and creating the strong CP problem. Before 't Hooft, physicists had wondered why there wasn't a ninth light pseudoscalar meson corresponding to the U1 axial symmetry. 't Hooft showed that instantons explicitly break this symmetry, giving the would-be ninth meson a large mass. But the same instanton effects that solve the U1 problem generate the theta term that creates the strong CP problem. The problem becomes even more puzzling when you consider how theta arises. The QCD vacuum has a complex topological structure. Gerard 't Hooft showed in the 1970s that the vacuum isn't simple, empty space, but rather a superposition of infinitely many distinct vacuum states, separated by energy barriers that quantum mechanics allows particles to tunnel through. This vacuum structure gives rise to the theta parameter naturally. There's no mechanism in standard physics to set theta to zero. When physicists encounter a fine-tuning problem like this, they generally seek one of three explanations. First, perhaps theta is constrained by some deeper symmetry we haven't yet discovered. Second, perhaps theta really is a random number, and we happen to live in a universe where it's small. This anthropic reasoning suggests that only in universes with small theta could complex structures like atoms and stars form. Third, perhaps theta isn't a fixed parameter at all, but a dynamical field that naturally evolves to zero. The third possibility led to what may be the most elegant solution to the strong CP problem, proposed in 1977 by two physicists at Stanford University. Their names were Roberto Pecci and Helen Quinn. The Pecci-Quinn solution and the birth of the axion Roberto Pecci and Helen Quinn approached the strong CP problem with a deceptively simple idea. What if theta, rather than being a fixed number, was actually a dynamical field, a quantity that could change and evolve? What if the laws of physics contained a mechanism that automatically drove theta to zero, eliminating CP violation in the strong force, regardless of its initial value? The elegance of their approach lay in converting an apparent defect of the theory into a feature. Instead of asking why theta happens to be zero, they proposed that theta must be zero because of a new symmetry in nature. The strong CP problem would solve itself, not through fine-tuning or coincidence, but through the inevitable dynamics of the theory. Their proposal introduced a new symmetry to the standard model, now known as the Pecci-Quinn symmetry, or simply PQ symmetry. This is a global symmetry, meaning it involves transformations that are the same everywhere in space, rather than varying from point to point. Specifically, it's a chiral symmetry, involving the way particles rotate in an abstract internal space. The chiral nature is crucial. It connects the symmetry to the axial currents that couple to the QCD vacuum structure. When the Pecci-Quinn symmetry is spontaneously broken, something remarkable happens. A new field appears in the theory, and this field couples to the QCD theta term in exactly the right way to cancel it. The potential energy of this field has its minimum precisely when the effective theta parameter equals zero. Like water finding its own level or a ball rolling to the bottom of a valley, the system naturally evolves toward the configuration that preserves CP symmetry. This mechanism is sometimes called the dynamical relaxation of theta. No matter what initial conditions the universe started with, no matter what value theta might have taken after the Big Bang, the dynamics of the PQ field would inevitably drive the effective theta to zero. The strong CP problem becomes not a puzzle of why theta is zero, but an inevitable consequence of the new symmetry. The key insight was that this new symmetry, when broken, would generate a field that couples to the theta term in QCD in exactly the right way. The potential energy of this field would have its minimum precisely when theta equals zero. Like a ball rolling to the bottom of a valley, the field would naturally evolve toward the value that cancels this IP-violating term. The strong CP problem would solve itself dynamically. in 1978, within months of Pecky and Quinn's paper, two theoretical physicists independently recognized a crucial consequence of this mechanism. Steven Weinberg at Harvard and Frank Wilczek at Princeton both realized that the breaking of the Pecky-Quinn symmetry would produce a new particle, a light boson that would emerge from the theory as naturally as photons emerge from electromagnetism. Wilczek gave the particle its name in a playful reference to a popular laundry detergent of the era. He called it the Axion, noting that it would clean up the theoretical mess created by the strong CP problem. Just as the detergent brand Axion promised to remove stubborn stains, the Axion particle would wash away the troublesome theta term. Weinberg had considered calling the particle the Higglet, referencing its similarities to the Higgs boson, but Wilczek's more colorful name stuck. The original Pecky-Quinn-Weinberg-Wilczek axion, often called the standard axion or PQW, axion had a mass of a few 100,000 electron volts and couplings strong enough that it should have been produced copiously in particle collisions and nuclear reactions. Experimentalists quickly searched for it, looking for unusual decays and reactions that would signal its presence, but the searches came up empty. Within a few years, the standard axion was ruled out by experiment. This might have been the end of the axion story, except for a crucial insight. In 1979 and 1980, several theorists, including Jin Kim, Andrei Sakharov, Mikhail Schiffman, Arkady Weinstein, Viktor Zakharov, Michael Dine, Willy Fischler, and Mark Srednitsky realized that the Pecky-Quinn mechanism didn't require the axion to have the specific mass and couplings that Weinberg and Wilczek had originally proposed. By introducing the PQ symmetry breaking at a much higher energy scale, far above the electroweak scale, the axion could be made much lighter and much more weakly interacting. These became known as invisible axions. Two classes of invisible axion models emerged as the most studied frameworks. The first, developed by Kim, and independently by Schiffman, Weinstein, and Zakharov, is called the KSVZ model, or hadronic axion model. In this scenario, the axion doesn't couple directly to ordinary quarks and leptons at tree level, but instead couples to new heavy quarks that carry both color charge and PQ charge. The ordinary particles we observe interact with the axion only through loop effects, making the couplings extremely small. The second class, developed by Dean, Fischler, and Srednitsky, and independently by Jitnitsky, is called the DFSZ model, or gut axion model, because it fits naturally into grand unified theories. In this scenario, the axion couples directly to ordinary quarks and leptons, but the couplings are suppressed by the very high PQ symmetry breaking scale. Both models share a crucial prediction. The axion mass and its coupling strength are not independent parameters. They're both determined by a single quantity, the axion decay constant, usually denoted F sub A. This decay constant represents the energy scale at which the PQ symmetry breaks. A larger decay constant means a lighter axion with weaker couplings. A smaller decay constant means a heavier axion with stronger couplings. The mathematical relationship is elegant. The axion mass, in electron volts, is approximately 6 times 10 to the minus 6, divided by the decay constant in units of 10 to the 12th giga-electron volts. If the decay constant is 10 to the 12 GeV, about 1 trillion times the proton mass energy, the axion mass is roughly 6 microelectron volts, a millionth of the electron mass. The axion would be extraordinarily light, lighter than any known particle except photons and neutrinos. This relationship between mass and coupling is crucial for experimental searches. It means that different search strategies probe different regions of the axion parameter space. Low-mass axions have weak couplings and require extremely sensitive detection techniques. Higher-mass axions have stronger couplings but face different experimental challenges. The entire landscape of axion physics is parameterized by a single number, the decay constant F sub A. The invisible axion escaped the early experimental constraints that ruled out the standard axion. It was too weakly interacting to be produced in accelerator experiments, too light to be detected in the nuclear physics measurements that had ruled out heavier axions. The invisible axion became, as its name suggests, invisible to early experimental probes. But theorists realized something remarkable about the invisible axion. Not only did it solve the strong CP problem, it might also solve another deep mystery in physics. The invisible axion, with its tiny mass and incredibly weak interactions, had all the properties needed to constitute the dark matter of the universe. Axions as dark matter, a cosmic coincidence. The realization that axions could be dark matter came gradually as theorists explored the cosmological implications of these hypothetical particles. What they found was striking. Under certain conditions, the early universe would inevitably produce a vast sea of axions with exactly the properties needed to explain the missing mass of the cosmos. This wasn't what theorists were looking for when they invented the axion. The particle was conceived purely to solve the strong CP problem, with no thought given to cosmological implications. The discovery that axions could also be dark matter was serendipitous, a beautiful example of theoretical physics, where a single hypothesis solves multiple unrelated problems. The key mechanism is called vacuum misalignment, or simply the misalignment mechanism. To understand it, we need to consider what happens to the axion field in the very early universe, in the first fractions of a second after the Big Bang, when temperatures exceeded trillions of degrees. In the moments after the Big Bang, the universe was extraordinarily hot and dense. The temperature was so high that even quarks and gluons existed as free particles in what's called a quark-gluon plasma. At temperatures above the PQ symmetry breaking scale, the psi-quin symmetry was unbroken, and the axion didn't exist as a particle. The field associated with the PQ symmetry was present, but it had no preferred value, no potential directing it to any particular state. As the universe expanded and cooled below the PQ symmetry breaking scale, the symmetry spontaneously broke. This is similar to how water freezes when cooled below 0 degrees Celsius. The high temperature state becomes unstable, and the system transitions to a new, lower energy state. When the PQ symmetry breaks, the axion field emerges with a definite value. But here's the crucial point. When the symmetry breaks, the axion field doesn't know where the minimum of its potential is. It settles into some random initial value, different in different regions of space, determined by the quantum fluctuations present at that moment. Think of it like a marble on a circular track. Before the symmetry breaks, the track is flat, and the marble can sit anywhere. When the symmetry breaks, a dimple appears somewhere on the track, marking the minimum energy position. But the marble is already sitting somewhere else, at whatever random position it happened to occupy. Only later will it roll toward the minimum. At high temperatures, QCD effects are suppressed, and the Axion potential is essentially flat. The Axion field remains frozen at its initial value, whatever that happened to be. The universe is expanding rapidly, and the expansion rate exceeds any rate at which the field might evolve. The Axion field is frozen in place, waiting. As the universe continues to cool and approaches the QCD phase, transition temperature, roughly 170 million electron volts, around a microsecond after the Big Bang, the Axion acquires a mass. QCD instanton effects generate a potential for the Axion field, a potential shaped like a tilted washboard with many equivalent minima. Now the Axion field begins to evolve. It starts oscillating around the nearest minimum of its potential, like a pendulum released from an angle. But there's a twist. The universe is expanding, and this expansion acts as friction on the oscillating field. The Axion oscillations don't dissipate into nothing. Instead, they behave as a collection of massive particles with zero average velocity, which is exactly the behavior of cold dark matter. The energy stored in these oscillations contributes to the mass energy of the universe. The amount depends on two factors: the initial misalignment angle, which determines how far from the minimum the field started, and the Axion mass, which determines when the oscillations began. If the misalignment angle is of order 1, meaning the field started roughly 1 radian away from the minimum, and if the Axion mass is in the microelectron volt to millielectron volt range, the resulting energy density matches the observed dark matter density. This is remarkable. The Axion wasn't invented to explain dark matter. It was invented to solve the strong CP problem. Yet it naturally produces the right amount of dark matter if its mass falls within a certain range. This is what physicists call a cosmic coincidence, though perhaps it's better described as a theoretical prediction that links two seemingly unrelated mysteries. The misalignment mechanism isn't the only way axions could potentially be produced in the early universe. If the PQ symmetry breaks after cosmic inflation, different regions of the observable universe would start with different initial misalignment angles. The boundaries between these regions would form topological defects called strings and domain walls. These defects would carry enormous energy and eventually decay, possibly producing additional axions. The contribution from string decay remains a subject of active research, with numerical simulations suggesting it could be comparable to or even exceed the misalignment contribution, though significant theoretical uncertainties remain in these calculations. There is also the possibility of thermal production. Even though axions interact very weakly with ordinary matter, in the hot, dense conditions of the early universe, some axions would inevitably be produced through collisions. These thermally produced axions would form relativistic background, a hot dark matter component that would have different cosmological effects than the cold axions from misalignment. However, the relative importance of thermal production compared to misalignment depends on details of the axion model that are not yet fully constrained. The cosmological considerations place important constraints on the axion parameter space. If the axion is too heavy, too many would be produced, exceeding the observed dark matter density and overclosing the universe. If the axion is too light, not enough would be produced to account for dark matter. The allowed range depends on cosmological assumptions, particularly whether inflation occurred before or after PQ symmetry breaking. In the pre-inflationary scenario, where inflation occurs after PQ symmetry breaks, the entire observable universe started with a single initial misalignment angle. This angle could be small by chance, allowing heavier axions that would otherwise overproduce dark matter. In the post-inflationary scenario, different regions have different angles, and the cosmic average is of order 1. This scenario more tightly constrains the allowed axion mass range. Current estimates, incorporating the latest QCD calculations and cosmological observations, suggest that if axions constitute all of the dark matter, their mass should be roughly in the range of 1 to 100 microelectron volts, depending on the cosmological scenario. This is the target range for many experimental searches. The Axions' status as a dark matter candidate received a boost from an unexpected direction: the failure of WIMP searches. For decades, WIMPs were the leading dark matter candidates, and enormous resources were devoted to finding them. Deep underground detectors reached sensitivities that should have revealed WIMPs if they existed with the masses and cross-sections predicted by popular theories. But the WIMPs never appeared. The parameter space for WIMP dark matter has been dramatically reduced, though not entirely eliminated. This has prompted theorists and experimentalists alike to take axions more seriously. There's also a theoretical appeal to axion dark matter that WIMPs lack. WIMPs are ad hoc in a sense. They're particles invented specifically to solve the dark matter problem. Axions, by contrast, solve two problems with one particle. They emerge from a theory designed to address the strong CP problem, and they just happen to have the properties needed for dark matter. This parsimony, solving multiple puzzles with minimal new physics, is aesthetically pleasing to many physicists and suggests that axions might be more than just a theoretical convenience. The early universe would have been flooded with axions produced through the misalignment mechanism, and possibly through string decay and thermal processes as well. These axions, fantastically light and extraordinarily weakly interacting, would have survived from those earliest moments to the present day. They would have contributed to the gravitational scaffolding around which galaxies formed. They would be passing through you right now, billions upon billions of them streaming through every cubic centimeter of space, utterly oblivious to the atoms and molecules that make up your body. If axions are the dark matter, they're not just out in a cosmos somewhere. They're here, permeating the very air you breathe, the chair you sit in, the planet beneath your feet. The challenge is detecting them. The properties of axions: a ghost-like particle. To understand why axions are so difficult to detect, we need to examine their properties in more detail. The axion is a spin-zero boson, a particle with no intrinsic angular momentum. It's electrically neutral and doesn't feel the strong or weak nuclear forces directly. Its interactions with ordinary matter are suppressed by the axion decay constant, which is at least 1 trillion times the proton mass. The mass of the axion is uncertain, but theoretical and observational constraints narrow the range. Laboratory experiments and astrophysical observations rule out axions with masses above about 1/10 of an electron volt. Cosmological considerations rule out axions much lighter than about 10 to the negative 22 electron volts. The theoretically preferred range if axions solve the strong CP problem and constitute dark matter, spans roughly from microelectron volts to millielectron volts. These masses are extraordinarily small. For comparison, the electron has a mass of about 500,000 electron volts. A microelectron volt axion would be 1,000,000,000 times lighter than an electron. The lightest known massive particles, neutrinos, have masses of at least a fraction of an electron volt. The axion, if it exists with the masses predicted by theory, would be by far the lightest massive particle known. The axion couples to ordinary matter and radiation through several channels, each characterized by its own coupling constant. The most important for detection is the axion-photon coupling. Through this coupling, an axion can convert into a photon in the presence of an external magnetic field, and vice versa. This Primakov effect, named after the physicist who first studied such processes, is the basis for most axion detection strategies. The axion-photon coupling strength is model-dependent. In KSVZ models, where the axion doesn't couple directly to ordinary quarks at tree level, the coupling is roughly 1 over the decay constant times a model-dependent coefficient of order unity. In DFSZ models, the coupling has a different coefficient and can even change sign depending on the ratio of Higgs field vacuum expectation values. Despite these variations, the coupling is always tiny, suppressed by the enormous decay constant. The axion also couples to electrons through an axion-electron coupling. This coupling is absent at tree level in KSVZ models, but present in DFS models. If axions couple to electrons, they can be produced in stellar cores through processes like bremsstrahlung, where axions are emitted when electrons scatter off nuclei. The axion-electron coupling is subject to stringent astrophysical constraints from observations of stellar evolution. Similarly, the axion couples to nucleons through an axion-nucleon coupling. This coupling is particularly relevant for the original motivation of the axion: solving the strong CP problem. The axion-nucleon coupling determines how the axion field affects the neutron electric dipole moment, driving it to zero and thereby solving the strong CP problem. Because all these couplings are suppressed by the decay constant, axions interact extraordinarily weakly with ordinary matter. A beam of axions could pass through the entire Earth without any of them interacting. The mean free path of an axion in ordinary matter is astronomical, far exceeding the diameter of the visible universe. This weakness of interaction is both a blessing and a curse for dark matter. It means axions would have decoupled from the primordial plasma very early, retaining their primordial abundance without being destroyed by interactions with ordinary matter. It also means they clump gravitationally without experiencing pressure or friction, forming the smooth, extended halos that observations suggest surround galaxies. But it also means detecting them is extraordinarily challenging. If axions constitute the dark matter halo of our galaxy, their local density near Earth is roughly 3 to 4/10 of a gigaelectron volt per cubic centimeter, or equivalently about 3 to 400 mega-electron volts per cubic centimeter. For microelectron volt axions, this corresponds to about 10 to the 14th axions per cubic centimeter, 100 trillion axions in every thimbleful of space. They're everywhere, but they're ghostly, passing through matter without leaving a trace. There's another remarkable property of axion dark matter that distinguishes it from other dark matter candidates. Because axions are so light, their number density is enormous. At such high densities, quantum effects become important. Instead of behaving like a collection of individual particles, dark matter axions form what physicists call a Bose-Einstein condensate, a coherent quantum state where all the particles occupy the same quantum state. In a Bose-Einstein condensate, the axion field behaves classically, oscillating coherently at a frequency determined by the axion mass. For a micro-electron-volt axion, this frequency is roughly 240 MHz in the radio frequency range. The dark matter halo of our galaxy would be permeated by an oscillating axion field, a cosmic radio signal too weak to detect by ordinary means, but potentially accessible to extremely sensitive instruments. This coherent oscillation has implications for detection. Instead of looking for rare scattering events between individual axion particles and detector atoms, as one would for WIMP dark matter, axion searches can look for the effects of the oscillating field as a whole. This is a fundamentally different detection strategy, and it's the basis for the most sensitive axion searches currently operating. The velocity distribution of dark matter axions also matters for detection. Axions in the galactic halo aren't at rest. They're orbiting the galaxy at velocities of roughly 200 kilometers per second, about 1,000th the speed of light. This velocity spread means the axion field isn't oscillating at a single sharp frequency, but rather over a range of frequencies spread around the central value. The width of this spread is about 1 part in a million, which determines the frequency resolution needed for axion searches. There's also the intriguing possibility, suggested by theoretical calculations, that dark matter axions aren't smoothly distributed but clumped into substructures. Axion mini-clusters could form in the early universe if the PQ symmetry breaks after inflation, seeded by the collapse of overdense regions. These hypothetical mini-clusters would have masses comparable to asteroids, but sizes much smaller, making them incredibly dense. If such structures exist, and if the Earth passed through one, the local dark matter density would temporarily spike, potentially producing a detectable signal in axion experiments. However, it should be noted that the existence and properties of mini-clusters depend on cosmological assumptions that remain uncertain, and their detection would itself constitute a major discovery about the nature of dark matter. Understanding these properties is essential for designing experiments to detect axions. The tiny couplings, the specific mass range, the coherent oscillation, the velocity distribution, the possibility of substructure. All these factors inform the experimental strategies that physicists have developed to hunt for these elusive particles. Searching for solar axions. The helioscope approach. One strategy for finding axions doesn't rely on dark matter at all. Instead, it exploits the fact that if axions exist, they should be produced in the cores of stars, including our own sun. The intense magnetic fields and high temperatures in stellar interiors provide the conditions needed for axions to be created through the Primakov effect, the conversion of photons to axions in the presence of electromagnetic fields. Stars are natural axion factories. Deep in the solar core, where temperatures exceed 15 million kelvins and densities reach 150 grams per cubic centimeter, conditions are extreme enough to produce exotic particles that would never appear under ordinary circumstances. Neutrinos stream out of the sun by the billions, produced in the nuclear reactions that power our star. If axions exist and coupled to photons, they too would be produced, though through a different mechanism. The Primakov effect occurs when a photon interacts with the electromagnetic field surrounding a charged particle, typically an ion or electron in the solar plasma. In this interaction, the photon can convert into an axion, which then escapes the sun. The probability of this conversion depends on the axion-photon coupling strength and on the local electromagnetic field environment. In the dense, hot solar core, these conditions are favorable for axion production. In the solar core, where temperatures exceed 15 million degrees and magnetic fields thread the plasma, photons constantly scatter off the electromagnetic fields of ions and electrons. Occasionally, instead of scattering, a photon converts into an axion. This axion, barely interacting with anything, streams outward unimpeded, escaping the sun in a fraction of a second rather than the tens of thousands of years it takes photons to random walk their way out. The contrast with photons is striking. A photon produced in the core of the sun travels only a tiny distance before being absorbed or scattered. Its path is a drunkard's walk, bouncing between particles, gradually diffusing outward over hundreds of thousands of years before finally reaching the surface and streaming into space. An axion, by contrast, flies straight out, passing through the entire mass of the sun as if it weren't there. The sun is essentially transparent to axions, a vast beacon of these hypothetical particles shining invisibly alongside its visible light. The sun would produce a steady flux of axions, peaking at energies of a few kilo-electron volts corresponding to the temperature of the solar core. The energy spectrum of solar axions follows a characteristic shape determined by the temperature profile of the solar interior and the energy-dependent production cross-section. Most solar axions would have energies between 1 and 10 kilo-electron volts, placing them in the X-ray range when they convert back to photons. These solar axions would rain down on Earth at a rate of roughly 10 to the 11 axions per square centimeter per second, assuming the axion-photon coupling is near the upper limits allowed by astrophysical constraints. Unlike solar neutrinos, which were successfully detected starting in the 1960s, solar axions have never been observed directly. The strategy for detecting solar axions is elegant. If axions can be created from photons in a magnetic field, they can also convert back into photons through the same process. Point a powerful magnet at the sun, and some of the incoming solar axions will convert to X-ray photons inside the magnet. Detect those X-rays, and you've found evidence for axions. This is the principle behind the axion helioscope, first proposed by Pierre Schiavone in 1983. A helioscope is essentially a magnetic telescope pointed at the sun. As solar axions stream through the magnetic field region, some convert to X-rays with the same energy as the original axions. X-ray detectors at the end of the magnet record any photons produced. The conversion probability depends on the strength and length of the magnetic field, the axion mass, and the axion-photon coupling. For a given magnetic field, longer is better. The axions have more opportunity to convert. Stronger fields also help, as the conversion probability scales with the square of the field strength. The probability also depends on whether the conversion is coherent, meaning all the conversions along the magnet length add constructively. This coherence is maintained as long as the axion and photon momenta are similar, which requires either that the axion mass is very small or that the magnet bore is filled with a gas that gives the photon an effective mass matching the axion mass. The most ambitious helioscope built to date is CAST, the CERN Axion Solar Telescope, located at the CERN laboratory near Geneva, Switzerland. CAST uses a decommissioned test magnet from the Large Hadron Collider, a superconducting dipole nearly 10 meters long, producing a field of 9 Tesla. The magnet is mounted on a platform that allows it to track the sun for about 90 minutes at sunrise and sunset each day. CAST began operations in 2003 and collected data for nearly 2 decades, with the primary solar axion search program concluding around 2021, though data analysis and additional detector runs continued afterward. In its first phase, with the magnet bores evacuated, CAST searched for very low mass axions. In later phases, the bores were filled with helium gas at varying pressures, allowing the experiment to scan through different axion masses by adjusting the effective photon mass. The results were null, but scientifically valuable. CAST found no evidence for solar axions, but it set increasingly stringent laboratory limits on the axion-photon coupling for axion masses up to about 1 electron volt. The 2017 results, published in Nature Physics, established an upper limit of roughly 0.66 times 10 to the negative 10 inverse giga-electron volts at 95% confidence level. More recent analyses, combining additional data runs through 2021 with advanced detectors, have pushed this limit even further, to approximately 5.8 times 10 to the negative 11 inverse giga-electron volts for axion masses below 0.02 electron volts. These bounds approach, and in some cases surpass, the constraints derived from astrophysical arguments about stellar energy loss, demonstrating that laboratory experiments can compete with indirect astronomical observations in constraining axion physics. At the heart of CAST's success are its advanced X-ray detection systems. The magnet has 2 bore tubes, and detectors are mounted at both ends to catch X-rays from axion conversion at sunrise and sunset. The detectors include X-ray telescopes that focus the signal onto small detector areas, improving the signal-to-noise ratio. The focusing optics, similar to those used in X-ray astronomy satellites, consist of nested mirror shells that reflect X-rays through grazing incidents. One of CAST's telescopes was actually recovered from a German space program. Despite its impressive sensitivity, CAST is limited by its relatively modest magnetic field volume. The conversion probability scales with the magnetic field strength squared times the length squared, so larger magnets would provide dramatically better sensitivity. This realization has driven plans for the next generation of axion helioscopes. The International Axion Observatory, or IAXO, represents the future of helioscope searches. Currently in the planning and development stages, IAXO will feature a purpose-built superconducting magnet 20 meters long with 8 bore tubes, each 60 centimeters in diameter. The magnetic field will average 2.5 Tesla, much larger in total volume than CAST, despite the lower field strength. Each bore will be equipped with focusing X-ray optics and low background detectors. IAXO's sensitivity will exceed CAST's by 1 to 1.5 orders of magnitude in the axion-photon coupling, corresponding to a factor of 100 to 1,000 in signal rate. This will allow IAXO to probe deeply into the parameter space predicted by axion models, potentially reaching the level where solar axions from DFSZ-type models should be detectable. Before IAXO reaches full operation, an intermediate stage called Baby IAXO will serve as a prototype and physics experiment in its own right. Baby IAXO, to be located at the DZY laboratory in Hamburg, Germany, will have two 10-meter-long magnet bores and detection systems similar to those planned for IAXO. With data taking expected to begin around 2028, Baby IAXO will already improve on CAST's sensitivity by about a factor of 5, entering new discovery territory. The helioscope approach has a significant advantage. It doesn't depend on axions being the dark matter. If axions exist and couple to photons, stars will produce them regardless of their cosmological role. A helioscope detection would confirm the existence of axions as particles, even if subsequent experiments revealed they don't constitute dark matter. This makes helioscopes complementary to dark matter searches, probing the axion parameter space from a different angle. But helioscopes have limitations. They're sensitive only to the axion-photon coupling, not to other axion properties. They can't directly measure the axion mass with precision. They can only set upper limits, or at best, determine that the mass falls within the coherence window for conversion. And they rely on a steady source of axions, the sun, which limits their instantaneous sensitivity. For searching for axion dark matter, specifically, a different experimental strategy is needed. One that exploits the properties of the dark matter halo surrounding our galaxy. This is the domain of the axion haloscope. Hunting dark matter. Axions, the haloscope revolution. If axions constitute the dark matter halo of the Milky Way, they're streaming through the Earth right now at an average velocity of about 230 kilometers per second and a local density of roughly 0.4 giga-electron volts per cubic centimeter. This corresponds to an enormous number of axions, perhaps 10 to the 14 particles per cubic centimeter for micro-electron volt masses. The challenge is detecting even one of them. The numbers involved are staggering. Every second, roughly 10 to the 23 axions pass through your body if they constitute the dark matter. That's comparable to the number of atoms in a few grams of matter, a truly astronomical flux. Yet because each axion interacts so weakly, the probability that any of them deposits energy in a detector is vanishingly small. The expected interaction rate is so low that conventional particle physics techniques, which work well for neutrinos or cosmic rays, are utterly inadequate for axion detection. The solution came from a brilliant insight by Pierre Schiavi in 1983. Rather than trying to detect individual axion interactions, Schiavi realized that one could exploit the wave-like nature of the axion field. Because dark matter axions are so light and so numerous, they form a coherent field, oscillating at a frequency determined by their mass. This oscillating field can resonantly excite a detector tuned to the same frequency, building up a measurable signal from countless tiny contributions. The haloscope, invented by Pierre Schiavi in 1983, is the leading technology for dark matter axion detection. The principle is the same as the helioscope. Axions convert to photons in a strong magnetic field via the Primakov effect. But instead of looking for solar axions, a haloscope looks for galactic dark matter axions. And instead of X-ray photons, it looks for microwave photons, because dark matter axions in the micro-electron volt mass range convert to photons with frequencies in the microwave band. The relationship between axion mass and photon frequency is direct and elegant. An axion of mass m converts to a photon of energy approximately equal to the axion rest mass energy, plus a small kinetic energy correction. For a microelectron-volt axion, this corresponds to a frequency of about 240 MHz, squarely in the radio frequency band. For heavier axions, the frequency is proportionately higher, extending into the microwave range for millielectron-volt masses. A haloscope consists of a high-quality microwave cavity immersed in a strong magnetic field. The cavity is a carefully machined metal chamber, typically cylindrical, designed to support electromagnetic standing waves at specific resonant frequencies. When the resonant frequency of the cavity matches the photon frequency that would result from axion conversion, the conversion is enhanced dramatically. This resonant enhancement is crucial. Without it, the signal would be far too weak to detect. The cavity acts as an antenna, accumulating the weak signal from many axion conversions and building it up to a detectable level. The enhancement factor depends on the cavity's quality factor, a measure of how many oscillations a photon makes before being absorbed by the cavity walls or leaking out through ports. High-quality cavities with quality factors of tens of thousands provide correspondingly large enhancements. Even with resonant enhancement, the signal power is still tiny, less than a yoctowatt, or 10 to the negative 24 watts. To put this in perspective, a yoctowatt is to a watt what a watt is to the total power output of the sun. It's an almost inconceivably small power level, but with sufficiently sensitive amplifiers and long integration times, it can be distinguished from the thermal noise background. The Axion Dark Matter Experiment, ADMX, at the University of Washington in Seattle, is the world's most sensitive haloscope. ADMX has been searching for axions since the 1990s and has undergone continuous upgrades to improve its sensitivity. The current generation, known as ADMX G2, features an 8 Tesla superconducting magnet, a large cylindrical copper-plated microwave cavity about 1 meter long and 50 centimeters in diameter, and a dilution refrigerator that cools the cavity to below 100 millikelvins. The key to ADMX's sensitivity is its amplifier technology. The first stage amplifier is a superconducting quantum interference device, or SQUID, that operates at the quantum noise limit. This means the amplifier adds the minimum possible noise allowed by the laws of quantum mechanics. Any less would violate Heisenberg's uncertainty principle. The SQUID amplifier, developed in collaboration with John Clark at the University of California, Berkeley, revolutionized axion searches by dramatically reducing the system noise temperature. ADMX searches for axions by slowly scanning the resonant frequency of its cavity. Adjustable tuning rods inside the cavity change the resonance, allowing ADMX to probe different axion masses over time. At each frequency setting, ADMX integrates the signal for a period determined by the expected signal strength and the noise level. The data are then analyzed for narrow band excess power that would indicate axion conversion. The search is painstaking. The axion mass is unknown, so ADMX must scan over a wide range of possible values. The expected signal is buried in noise, so each frequency bin requires long integration. The cavity must be tuned in small steps to avoid missing a signal that falls between measurement points. A single scan can take years to complete. Despite these challenges, ADMX has achieved remarkable results. Over multiple data-taking campaigns, spanning years, the experiment has systematically excluded axions with KSVZ couplings across a growing range of masses, including regions between roughly 2.7 and 4.2 microelectron volts in earlier runs, and more recently, extending up to about 5.4 microelectron volts. Even more significantly, ADMX has achieved the sensitivity necessary to probe DFSZ axions, those with weaker couplings, predicted by the Dine-Fischler-Srednitsky-Jetnitsky model, in select mass windows. This represents a milestone in axion physics, as DFSZ axions were previously beyond experimental reach. While no detection has yet occurred, each null result progressively constrains the parameter space where dark matter axions might hide. Based on current scanning rates and planned upgrades, if dark matter axions exist with masses in the microelectron volt range and with couplings predicted by standard QCD axion models, there is reason to believe that ADMX or similar experiments could find them within the coming decade. ADMX isn't the only haloscope in operation. The Center for Axion and Precision Physics Research, KIAP, in South Korea, operates several haloscopes probing different mass ranges. KIAP's experiments use high-field magnets and advanced detector technologies, achieving sensitivities competitive with ADMX in some frequency bands. Other haloscopes include Haystack at Yale University, which uses quantum noise evading techniques to enhance sensitivity, and the Orpheus and Organ experiments that target specific mass windows. The haloscope technique faces a fundamental challenge at higher frequencies. The resonant cavity must have dimensions comparable to the wavelength of the converted photons. For microelectron volt axions, this wavelength is about a meter, manageable for cavity construction. But for heavier axions in the millielectron volt range, the wavelength shrinks to millimeters or less. Building high-quality cavities at these scales is difficult, and the cavity volume decreases, dramatically reducing the signal power. Various approaches are being developed to extend haloscope searches to higher masses. Multiple small cavities can be combined to increase the effective volume. Dielectric haloscopes use stacks of dielectric disks instead of metal cavities, maintaining larger volumes at higher frequencies. Metamaterial haloscopes exploit exotic material properties to concentrate the conversion. These novel concepts are at various stages of development and deployment. There's also the question of what happens if ADMX and other haloscopes don't find axions in the microelectron volt range. Either axions don't constitute dark matter, their mass lies outside the searched range, or the axion-photon coupling is weaker than expected. All these possibilities would have profound implications for particle physics and cosmology. A null result would narrow the parameter space, guiding future theoretical and experimental efforts. The haloscope approach has a major advantage. It directly searches for the dark matter component of the axion field. A detection would simultaneously confirm the existence of axions and establish that they constitute at least part of the dark matter. The signal would also carry information about the local dark matter velocity distribution, providing a window into the structure of our galactic halo. The dream scenario for axion hunters is a positive signal, a narrow spike of excess power at a specific frequency, persisting over time, correlating with the expected modulation from the Earth's motion through the galactic halo. Such a discovery would represent a major breakthrough in physics, solving both the strong CP problem and the dark matter mystery with a single particle. Until that day comes, experimentalists continue their patient scan through the cosmos of possible axion masses, light shining through walls, laboratory, axion searches, while helioscopes look for solar axions and haloscopes hunt dark matter axions. A third approach seeks to produce and detect axions entirely in the laboratory without relying on any cosmic source. These light shining through wall experiments, or LSW experiments, exploit the same Primakov conversion that underlies the other axion searches, but in a controlled environment where the axion source is a laser beam rather than the sun or the galactic halo. The appeal of laboratory searches is their independence from astrophysical assumptions. When searching for solar axions, we must trust our models of the solar interior. When hunting dark matter axions, we assume that axions constitute the local dark matter density. A laboratory experiment makes and detects its own axions, with no reliance on distant or uncertain sources. If something shows up, we know exactly what it is and where it came from. The concept is elegantly simple, at least in principle. A powerful laser beam passes through a strong magnetic field. Some fraction of the photons convert to axions through the Primakov effect. These axions, interacting so weakly with matter, pass through an opaque wall that completely blocks the remaining photons. On the other side of the wall, another magnetic field region converts some of the axions back into photons. Detecting these regenerated photons would be evidence that something traversed the wall, something that can convert to and from light in magnetic fields, something with the properties of an axion. The name captures the apparent magic. Light shines through an impenetrable barrier. Of course, it's not light that passes through, but axions, which then become light again on the other side. But the net effect is that photons enter one side and photons emerge from the other, despite an opaque obstacle in between. It's like a magic trick, except the magic is real physics, operating at the frontier of our knowledge. The idea for such experiments dates back to the mid-1980s, shortly after Sakivi proposed the helioscope and haloscope concepts. Several groups realized that the same physics could be exploited in a laboratory setting, using lasers as the photon source rather than the sun. The first light shining through wall experiments were conducted in the late 1980s and early 1990s. Achieving sensitivities that ruled out some early axion models, but not the invisible axions favored by theoretical considerations. The challenge is that the conversion probability is tiny. Even with powerful magnets and intense lasers, the chance that a photon converts to an axion, traverses the wall, and converts back to a photon is extraordinarily small. The probability of each conversion scales with the square of the axion-photon coupling, so the overall probability scales with the fourth power of the coupling. For axion couplings near current experimental limits, this probability might be 10 to the negative 20 or less. One photon regenerated for every 100 billion photons sent in. To detect such rare events requires heroic, experimental measures. The laser must be extraordinarily powerful. The magnets must be as strong and as long as possible. The detector must be sensitive to single photons while rejecting all background noise. And clever optical techniques must be employed to enhance the signal beyond what brute force alone could achieve. The ALPS experiment at the Deswey Laboratory in Hamburg, Germany, represents the state-of-the-art in light shining through wall searches. ALPS 2, the current version, uses 24 superconducting dipole magnets salvaged from the Hera accelerator, 12 on each side of the wall. These magnets, each about 9 meters long, were originally curved for the particle accelerator, but have been straightened for ALPS. They produce a magnetic field of about 5.5 Tesla over a total length of about 120 meters on each side. The key innovation in ALPS 2 is the use of optical resonators. An optical cavity on the production side bounces the laser beam back and forth thousands of times, effectively increasing the power available for axion production. On the regeneration side, another optical cavity enhances the probability that any returning axion will convert to a photon. The combination of these resonant enhancement factors boosts the expected signal by about 8 orders of magnitude compared to a single-pass experiment. The laser system, developed at the Max Planck Institute for Gravitational Physics in Hanover, produces a narrow bandwidth, highly stable beam that can be precisely locked to the cavity resonance. The detection system must distinguish any regenerated photons from the overwhelming background of stray light, detector noise, and other spurious signals. The expected signal rate, even with all enhancements, is less than 1 photon per day. ALPS 2 began science operations in May 2023 with an initial data-taking run, followed by a more extensive science campaign from February to May 2024. The first results, published in late 2024, found no evidence for axions, but achieved a sensitivity of approximately 1.5 times 10 to the negative 9 inverse gigaelectron volts, representing more than a 20-fold improvement over all previous light shining through wall experiments. As the collaboration continues to upgrade the optical systems, ALPS 2 is expected to improve its sensitivity by another 2 orders of magnitude, potentially reaching deep into parameter space predicted by some axion models. The light shining through wall approach has a distinct advantage. It produces axions in a controlled way, with known properties, rather than relying on astrophysical assumptions. The mass and energy of the axions are determined by the laser wavelength and the experimental geometry. The flux is determined by the laser power and conversion probability. If a signal is seen, it can be characterized in detail by varying the experimental parameters. LSW experiments also probe a broader class of particles than just the QCD axion. Any particle that couples to 2 photons, such as the axion-like particles that appear in many extensions of the standard model, could produce a signal. This makes LSW experiments sensitive to a wide range of new physics, not just the specific particle that solves the strong CP problem. However, LSW experiments have limitations. The conversion probability depends on the 4th power of the axion-photon coupling, twice for production and twice for detection, making the sensitivity scale unfavorably with coupling strength. The experiments are also limited by the available magnetic field strength and length. Even with the largest practical magnets, LSW experiments can't reach the sensitivity of helioscopes or haloscopes for the specific axion models that best fit cosmological observations. Beyond ALPS, other LSW experiments have operated or are planned. The OSCAR experiment at CERN used LHC magnets to search for axion-like particles. The proposed Jura project would use X-rays instead of optical photons, probing higher mass axions. Various tabletop experiments search for axion-like particles in different mass and coupling ranges. The light shining through wall technique complements other search strategies. It doesn't require dark matter to consist of axions and doesn't depend on the properties of stellar interiors. It's a purely laboratory-based test of the axion hypothesis. A positive signal in an LSW experiment would be strong evidence for axion-like particles, while continued null results constrain the parameter space available to these hypothetical entities. Astrophysical constraints, what the stars tell us. Long before laboratory experiments could probe the axion parameter space, astrophysical observations had already placed powerful constraints on axion properties. Stars, it turns out, are extraordinarily sensitive probes of new physics. If axions exist and coupled to ordinary matter, they would be produced in stellar interiors and carry away energy, affecting stellar evolution in potentially observable ways. The astrophysical approach to constraining axions exemplifies a beautiful interplay between particle physics and astronomy. We can't build a star in the laboratory, can't directly measure what happens in stellar cores, but we can observe the accumulated effects of stellar evolution over millions and billions of years. Any departure from standard physics would leave signatures in the properties of stars we observe today, subtle fingerprints that careful analysis can detect. The argument is straightforward in principle. Stars shine because nuclear reactions in their cores release energy. This energy slowly diffuses outward through the stellar interior, transported by radiation and convection, eventually escaping from the stellar surface as the light we observe. The rate at which energy escapes determines the star's luminosity, and the star adjusts its internal structure to maintain a balance between energy generation and energy loss. If there's an additional channel for energy loss, such as axion emission, the balance is disrupted. The star must burn its nuclear fuel faster to maintain equilibrium, compensating for the extra energy drain. This faster burning has observable consequences. It shortens the star's lifetime, changes its luminosity at various evolutionary stages, and alters the ratios of stars in different phases of evolution within stellar populations. The physics of axion production in stars depends on which axion coupling dominates. If axions couple primarily to photons, they're produced through the Primakov effect, similar to solar axion production, but potentially at different rates depending on stellar conditions. If axions couple to electrons, they're produced through Bremsstrahlung, the radiation emitted when electrons scatter off nuclei. If axions couple to nucleons, they're produced through nuclear Bremsstrahlung or through interactions involving the strong force. Each coupling leads to different production rates in different stellar environments, and thus different constraints emerge from different types of stars. The art of extracting axion bounds from stellar observations lies in identifying which stars and which evolutionary phases are most sensitive to which couplings. The most sensitive stellar probes of axion physics are helium-burning stars and cooling stellar remnants, horizontal branch stars and globular clusters, red giants approaching helium ignition, and white dwarfs in various stages of cooling, all provide constraints on axion couplings. Each type of star probes a different aspect of axion physics, and together they map out the allowed parameter space with remarkable precision. Consider white dwarfs, the dense remnants of stars like our Sun. After exhausting their nuclear fuel, these stellar corpses slowly cool over billions of years, radiating away their stored thermal energy. The cooling rate depends on the star's heat capacity and its energy loss mechanisms. Normally, white dwarfs cool by radiating photons from their surfaces and at high temperatures by emitting neutrinos from their cores. If axions couple to electrons, they would be produced in white dwarf interiors through Bremsstrahlung, the radiation emitted when electrons scatter off ions. These axions would escape freely, carrying energy out of the star and accelerating the cooling process. Observations of the white dwarf luminosity function, the distribution of white dwarf brightnesses in the galaxy, can test whether white dwarfs cool faster than expected. Studies of white dwarfs in globular clusters like 47 Tucanae, where all the stars formed at approximately the same time, provide particularly clean tests. Recent analyses using Hubble Space Telescope observations have set limits on the axion-electron coupling. One 2023 study found no evidence for axion cooling in the white dwarf population, setting a constraint on the axion-electron coupling at approximately 0.81 times 10 to the negative 13 at 95% confidence level. This is more stringent than previous limits and excludes some parameter ranges that had been suggested by hints of anomalous cooling in other stellar samples. However, it should be noted that different analyses of different stellar populations sometimes yield different results, and the interpretation depends on the accuracy of stellar models used in the comparison. Red giant branch stars provide another constraint. As low-mass stars exhaust hydrogen in their cores, they evolve onto the red giant branch, with a shell of hydrogen burning around an inert helium core. The core gradually contracts and heats until helium ignition occurs in a dramatic event called the helium flash. The luminosity at which this flash occurs, marked by the tip of the red giant branch, depends on the core mass at ignition. If axions are produced in the red giant core through the Primakov effect, they would carry energy away and delay helium ignition, allowing the core to grow more massive before the flash. This would make the tip of the red giant branch brighter than expected. Observations of globular clusters constrain the axion photon coupling through this mechanism at roughly 10 to the negative 10 inverse gigaelectron volts, comparable to the CAST laboratory limits. Horizontal branch stars, which burn helium in their cores after the red giant phase, provide complementary constraints. Axion emission would shorten the helium burning lifetime, changing the ratio of horizontal branch to red giant stars observed in globular clusters. The so-called R parameter, this ratio, has been measured in many clusters and constrains axion couplings at a similar level. There's also the supernova constraint. When a massive star collapses to form a neutron star, it releases an enormous amount of energy in the form of neutrinos. The 1987A supernova in the Large Magellanic Cloud provided a rare opportunity to observe these neutrinos directly. If axions were produced copiously in the protoneutron star, they would have shortened the duration of the neutrino burst. The observed burst duration of roughly 10 seconds constrains the axion nucleon coupling and, indirectly, the axion mass. Intriguingly, some astrophysical observations suggest hints of excess cooling that could be explained by axions. Several pulsating white dwarfs show period changes faster than expected from standard cooling models. The white dwarf luminosity function in the galactic disk shows a subtle deficit of hot white dwarfs compared to models. Red giant observations in some clusters show slight tensions with predictions. These hints are tantalizing but not conclusive. Systematic uncertainties in stellar modeling, observational errors, and the difficulty of comparing diverse stellar samples make it hard to claim definitive evidence for anomalous cooling. The hints have motivated increased attention to axion physics, but haven't convinced the community that axions have been detected indirectly. The astrophysical bounds on axion couplings are among the strongest constraints available, often exceeding laboratory limits by orders of magnitude. They arise from the sheer size and energy of stellar systems. Stars convert enormous amounts of mass to energy over their lifetimes, and even tiny axion couplings can have significant effects integrated over millions or billions of years. But astrophysical arguments have limitations. They depend on detailed models of stellar interiors, which involve complex physics, including nuclear reactions, convection, opacity, and magnetic fields. Systematic errors in these models could affect the derived constraints. Laboratory experiments, while less sensitive in some regions of parameter space, provide cleaner tests that don't rely on astrophysical assumptions. The combination of astrophysical and laboratory constraints defines the allowed parameter space for axions. For the QCD axion specifically, the constraints point to a preferred mass range, heavy enough that astrophysical cooling bounds are satisfied, light enough that laboratory and cosmological constraints are met. This window, roughly from micro-electron volts to milli-electron volts, is exactly where dark matter axion searches are focused. The Axiverse and string theory predictions. The QCD axion, solving the strong CP problem and potentially constituting dark matter, is remarkable enough. But theoretical developments over the past 2 decades have revealed that axions may be far more prevalent in nature than originally imagined. String theory, the leading candidate for a unified theory of all forces and particles, predicts not just one axion, but potentially hundreds, spanning many orders of magnitude and mass. This scenario has become known as the Axiverse. The Axiverse represents one of the most striking predictions to emerge from theoretical work on string theory in recent decades. It should be emphasized that this remains a speculative scenario, as string theory itself has not yet been experimentally confirmed. However, if string theory provides an accurate description of nature, the Axiverse could leave observable signatures at low energies, potentially providing indirect evidence for this framework of physics beyond the standard model. The absence of such signatures, conversely, would constrain which string compactifications might describe our universe. String theory attempts to describe all particles and forces as different vibrational modes of tiny one-dimensional objects called strings. These strings are unimaginably small, with lengths on the order of the Planck scale, about 10 to the negative 33 centimeters. The theory is mathematically beautiful and internally consistent, providing a quantum mechanical description of gravity that has eluded other approaches. But string theory also requires features that seem strange from the perspective of ordinary experience. To make the mathematics consistent, string theory requires extra dimensions beyond the 3 spatial dimensions and one-time dimension we observe. Specifically, string theory requires either 10 or 11 total spacetime dimensions, depending on the version. These extra dimensions aren't hidden by being small in the usual sense, but are thought to be compactified, curled up into complex geometric shapes at scales too small to observe directly with current technology. The topology of these compactified dimensions determines many properties of the particles we observe. The shape of the extra dimensions, characterized by mathematical objects like Calabi-Yau manifolds, determines the masses and couplings of particles in the four-dimensional theory we experience. Different compactifications lead to different effective theories, with different particle content and different physics. In particular, certain topological features, called cycles, can support light scalar fields that behave much like axions. These fields arise naturally from the higher dimensional gauge fields of string theory, when the theory is compactified to 4 dimensions. They emerge not because theorists added them by hand, but because the mathematics of compactification inevitably produces them. The number of such axion-like particles depends on the complexity of the compactification. In simple scenarios, there might be a handful of axions. In more elaborate compactifications with complex Calabi-Yau manifolds, the number can reach into the hundreds. These particles span a vast range of masses, from milli-electron volts down to cosmological scales where the mass might be 10 to the negative 22 electron volts, or even smaller. Each axion-like particle would have its own coupling constants and its own potential role in cosmology. The Axiverse scenario, if realized in nature, would have profound implications for cosmology. Different axions in such a scenario would begin oscillating at different times in cosmic history, potentially contributing to dark matter with different properties. The lightest axions, with masses around 10 to the negative 22 electron volts, would behave as what theorists call fuzzy dark matter, a form of dark matter whose quantum wavelength is macroscopic, potentially reaching kiloparsec scales. Fuzzy dark matter, if it exists, would smooth out small-scale structures in the universe, potentially resolving some tensions between observations and standard cold dark matter predictions, though the observational situation remains debated among astronomers. Heavier axions in the Axiverse could constitute more conventional cold dark matter, while the QCD axion specifically would still solve the strong CP problem. The Axiverse thus provides a rich phenomenology with multiple dark matter components at different masses and with different couplings. Testing the Axiverse scenario is challenging because it predicts such a wide range of masses and couplings. Different experimental techniques are needed to probe different regions of the Axiverse parameter space. Haloscopes search for axions in the microelectron volt range. Helioscopes and LSW experiments probe heavier axion-like particles. Cosmological and astrophysical observations constrain both the heavy and ultralight ends of the spectrum. Black hole superradiance provides a particularly interesting theoretical constraint on axions in certain mass ranges. According to general relativity, rotating black holes can in principle spin down by transferring energy to light bosons through a quantum effect, analogous to stimulated emission. If an axion exists with a Compton wavelength comparable to the black hole's size, the black hole would rapidly lose angular momentum, spinning down much faster than expected. Observations of rapidly spinning black holes can therefore, in principle, exclude axions in specific mass ranges, though these constraints rely on assumptions about black hole formation and evolution that carry their own uncertainties. For stellar mass black holes, the relevant axion masses are around 10 to the negative 12 electron volts. For supermassive black holes, the masses are much lower, around 10 to the negative 18 electron volts. The observation of rapidly spinning black holes across these mass scales provides constraints on the Axiverse, ruling out certain populations of axion-like particles. Gravitational wave observations offer another window on the Axiverse. Axion clouds around black holes could produce continuous gravitational wave signals as the cloud oscillates. The LIGO and Virgo detectors, which have successfully detected gravitational waves from black hole and neutron star mergers, could potentially detect these continuous signals if the axion mass happens to fall in the right range and the source is close enough. The Axiverse also has implications for inflation, the hypothetical period of rapid expansion in the very early universe. Some string theory scenarios predict that one or more axion-like fields drove inflation, determining the seeds for cosmic structure that we observe today. The spectrum of primordial perturbations imprinted on the cosmic microwave background and the distribution of galaxies could carry signatures of these inflationary axions. More speculatively, axion-like particles might explain other puzzles in physics. Some researchers have suggested that axions could solve the matter-antimatter asymmetry problem, explaining why the universe contains more matter than antimatter. Others have proposed axion explanations for certain anomalies in astrophysical observations, such as the transparency of the universe to high-energy gamma rays or the cooling of neutron stars. The string Axiverse represents a theoretical prediction that, if confirmed, would provide evidence for string theory itself. Detecting multiple axion-like particles at different masses would suggest that the universe has extra dimensions with complex topology, exactly as string theory predicts. This would be one of the few ways to test string theory experimentally, given that the typical energy scale of string effects is far beyond the reach of particle accelerators. For now, the Axiverse remains a theoretical possibility, neither confirmed nor ruled out. The search for axions, in all their potential variety, continues across multiple experimental frontiers. Each null result narrows the parameter space, while each hint or anomaly raises the possibility that discovery is imminent. The cosmic impact of axions. If axions exist and constitute dark matter, their influence on the universe is profound and pervasive. Dark matter shaped the cosmos from its earliest moments, providing the gravitational scaffolding around which ordinary matter collected to form galaxies, stars, and ultimately the planets and life forms that ponder their own existence. In the first moments after the Big Bang, the universe was a nearly uniform soup of particles and radiation, but tiny fluctuations in density, seeded perhaps by quantum effects during inflation, provided the starting point for cosmic structure. Regions with slightly higher density attracted matter gravitationally, growing denser over time. Regions with lower density became emptier, eventually forming the voids that separate galaxy clusters today. Dark matter dominated this process. Ordinary matter, interacting strongly with radiation, was prevented from clumping until the universe had cooled enough for atoms to form, roughly 380,000 years after the Big Bang. Dark matter, interacting only gravitationally, began clumping much earlier. By the time ordinary matter was released from its radiation bath, dark matter had already formed a web of structures, gravitational wells, into which ordinary matter could fall. Axion dark matter would have behaved much like any other cold dark matter during this structure formation era. The tiny random velocities of dark matter particles, whether axions or WIMPs, meant they clustered freely without pressure support. Computer simulations of cosmic structure formation, which successfully reproduce the observed distribution of galaxies and galaxy clusters, don't distinguish between different cold dark matter candidates at large scales. But axion dark matter might behave differently at small scales. Because axions are so light, their de Broglie wavelength can be macroscopic. For microelectron volt axions, this wavelength is about a meter, too small to matter for galactic dynamics. But for ultralight axions in the fuzzy dark matter regime, with masses around 10 to the negative 22 electron volts, the de Broglie wavelength reaches kiloparsecs. At these scales, the wave nature of the axion field suppresses structure formation, potentially smoothing out the centers of galaxies and reducing the number of small satellite galaxies. Some observations suggest there might be fewer small galaxies than predicted by standard cold dark matter models. The cores of galaxies also appear smoother than simulations predict. These small-scale challenges to cold dark matter have been cited as possible evidence for fuzzy dark matter, though other explanations involving ordinary astrophysical processes remain possible. If axions form the dark matter halo of our Milky Way, they're passing through the solar system right now. The density near Earth is about 0.4 giga-electron volts per cubic centimeter, corresponding to trillions of axions per cubic centimeter. They're streaming through your body as you listen to these words, utterly oblivious to the atoms that constitute you. The axion wind has a directionality imposed by the Earth's motion through the galactic halo. The Sun orbits the center of the Milky Way at about 230 kilometers per second, and the Earth's orbital motion adds a yearly modulation to the apparent velocity. This modulation, about 30 kilometers per second in amplitude, could in principle be detected by sensitive experiments as a yearly variation in signal strength. Within galaxies, axion dark matter would form smooth, extended halos, denser toward the centers and thinning out with distance. Ordinary matter, attracted by the gravity of these halos, would sink to the center and form the visible galaxy. The stars and gas we observe are embedded within invisible dark matter halos, many times more massive than the visible material. Some theoretical work suggests that axion dark matter might form coherent structures within the halo. Bose-Einstein condensation could lead to axion stars, dense concentrations of axion field energy. Tidal streams from disrupted satellite galaxies might be visible in the axion field as well as in ordinary matter. The axion field oscillation, coherent over macroscopic distances, could produce interference patterns at the boundaries of different velocity streams. The cosmological implications of axions extend beyond dark matter. If the Pecci-Quinn symmetry breaking occurred after inflation, the universe today would contain cosmic strings, one-dimensional topological defects left over from the phase transition. These axion strings would be too faint to detect directly, but their decay products might contribute to the axion dark matter density or produce other observable signatures. Domain walls, two-dimensional defects, could also form under certain conditions. The fate of these walls depends on the details of the axion potential. If walls survive to late times, they would dominate the energy density of the universe, contradicting observations. This cosmological domain wall problem constrains Axion models, requiring that the potential have a single minimum, or that walls decay quickly enough to avoid domination. The study of Axion cosmology has become a rich subfield, with simulations, calculations, and observations all contributing to our understanding. Each piece of evidence, whether positive or negative, refines our picture of what axions are, how many there are, and what role they play in the cosmos. The future of Axion research. We stand at a pivotal moment in the search for axions. After decades of theoretical development and experimental effort, the tools to definitively test the axion hypothesis are coming online. The next decade promises either discovery or decisive constraints that would reshape our understanding of particle physics and cosmology. ADMX and other haloscopes are scanning the micro-electron-volt mass range with sensitivity to detect DFZ axions, the weaker of the two canonical models. If dark matter consists of QCD axions in this mass range, detection could come at any time. Each frequency bin scanned either finds the signal or rules out that specific mass with high confidence. The search is systematic, patient, and progressively more sensitive. Baby EXO, scheduled to begin operations around 2028, will push helioscope sensitivity into new territory. For the first time, a helioscope will probe axion photon couplings below the astrophysical bounds, testing whether our understanding of stellar physics is complete. A positive signal would be revolutionary. A null result would strengthen the astrophysical constraints and further narrow the allowed parameter space. ALPS 2 has begun searching for axion-like particles with the highest power light shining through wall experiment ever constructed. While the sensitivity doesn't reach the QCD axion band, ALPS2 will test extensions of the standard model that predict additional axion-like particles. The techniques developed for ALPS2 could inspire future experiments with even greater sensitivity. Beyond these flagship experiments, numerous smaller efforts probe different regions of parameter space. The Abracadabra experiment searches for axion-induced magnetic field oscillations. The Casper experiments use nuclear magnetic resonance techniques. The QUAX experiment in Italy pushes to higher frequencies. The Organ experiment in Australia targets a specific mass range suggested by some cosmological models. Theoretical developments continue to refine predictions and suggest new search strategies. Precision calculations of the QCD axion mass and couplings narrow the target range for experiments. String theory compactifications provide specific predictions for the axiverse that can be tested observationally. Quantum sensing techniques borrowed from precision measurement and quantum information science offer new ways to detect the feeble signals from axion conversion. Astrophysical observations provide independent constraints and potential hints. Future space telescopes will measure stellar populations with unprecedented precision, testing cooling predictions. Gravitational wave detectors might detect axion clouds around black holes. Cosmological surveys will map the distribution of matter in the universe with exquisite detail, testing whether dark matter behaves exactly as cold dark matter should or shows the wave-like signatures expected from ultralight axions. The convergence of these diverse approaches creates a realistic prospect for answering the fundamental questions. Do axions exist? If so, what are their properties? Do they constitute dark matter? Do they solve the strong CP problem? Are there multiple axion-like particles, as string theory suggests? A positive detection would mark one of the great discoveries in the history of physics. It would solve two fundamental problems: the strong CP problem and the dark matter mystery, with a single particle. It would open a new window on the universe, revealing an invisible component that shapes cosmic structure. And it would provide evidence for physics beyond the standard model, pointing the way toward deeper theories. Even a comprehensive null result would be profoundly informative. If searches exhaust the natural parameter space for QCD axions, without detection, physicists would need to reconsider the strong CP problem. Perhaps the theta parameter really is zero by coincidence or anthropic selection. Perhaps there's another solution we haven't yet imagined. The absence of axion dark matter would similarly demand new explanations for the cosmic missing mass, reinvigorating searches for other candidates. The history of physics is filled with theoretical predictions that took decades to confirm, from neutrinos to the Higgs boson. The axion has already waited nearly 50 years since its theoretical birth. The tools to find it, or to determine it doesn't exist, are finally at hand, contemplating the invisible. As we conclude our journey through the world of axion physics, let us step back and contemplate what it means to search for something so profoundly invisible. The axion, if it exists, is all around us right now. Trillions of these particles are passing through every centimeter of your body every second. They've been streaming through the Earth for billions of years, since before the Sun formed, since before the Milky Way itself coalesced from the primordial gas. They shape the very galaxy in which we live, providing the gravitational structure around which ordinary matter collected. The stars that forged the atoms in your body were themselves formed in the gravitational wells of dark matter halos. In a very real sense, if axions are the dark matter, you owe your existence to them. Yet you cannot see them, cannot feel them, cannot detect them through any of your senses or any ordinary instrument. They pass through matter as if it weren't there, interacting so weakly that a single axion could traverse the entire observable universe without touching a single atom. Their presence is known only through their collective gravity, shaping the cosmos on the largest scales, while remaining utterly invisible on human scales. There's something humbling about this. The matter we can see and touch, the atoms and molecules that make up our bodies and our world, constitute only a small fraction of what exists. The universe is vastly larger and stranger than our everyday experience suggests. Most of reality is hidden from us, accessible only through the careful logic of physics and the ingenious devices of experimentalists. The search for axions exemplifies the best of science, a puzzle arising from deep theoretical considerations, a prediction of new phenomena, and a decades-long effort to test that prediction with ever more sophisticated experiments. Whether axions are found or not, the search itself advances our understanding of nature. The techniques developed to hunt for axions have applications in quantum sensing, precision measurement, and fundamental physics. The theoretical work has illuminated connections between particle physics, cosmology, and string theory. Science proceeds not by certainty, but by narrowing uncertainty. Each experiment that fails to find axions doesn't prove they don't exist. It merely constrains where they can hide. Each theoretical calculation refines our expectations. Each observation of stars and galaxies provides new data to compare with predictions. Gradually, patiently, the landscape of possibilities is mapped and the truth is approached. The history of physics is replete with examples of particles that took decades to find after their theoretical prediction, from the neutrino proposed in 1930 and finally detected in 1956, to the Higgs boson predicted in 1964 and discovered in 2012. The axion, proposed in 1977 and still sought nearly 5 decades later, may yet join this honored list of elusive particles finally revealed. Perhaps in the coming years, a detector somewhere will register the faint signal of axion conversion, photons appearing where none should be, power deposited in a microwave cavity that can only be explained by the invisible becoming briefly visible. The discovery would vindicate a half-century of theoretical insight and experimental effort. It would solve profound mysteries about the nature of matter and the structure of the cosmos. Or perhaps the searches will continue to find nothing, and physicists will be forced to conclude that nature chose a different path, that the strong CP problem has some other solution, that dark matter is made of something entirely unexpected. This too would be valuable, guiding the search in new directions. Either way, the quest itself is ennobling. To reach out with our instruments toward the invisible, to seek understanding of what we cannot directly perceive, to build theories and test them against the universe. This is what makes us human. The axion may be ghostly, ethereal, all but impossible to detect, but our determination to find it, or to understand why we cannot, speaks to something essential about the scientific enterprise and the human desire to comprehend the fundamental nature of reality. We are creatures who ask why, who seek the patterns in chaos, who refuse to accept mystery as final. The night sky, with its thousands of visible stars, is beautiful. But knowing that those stars are embedded in vast halos of invisible matter, that the gravity shaping the cosmos comes mostly from something we cannot see, that trillions of ghost particles might be streaming through us right now. This knowledge makes the universe stranger and more wonderful than unaided eyes could ever reveal. The search for axions reminds us that there is always more to learn, more to discover, more to wonder at in this vast and ancient cosmos we call home. Thank you for joining me on this exploration of axion physics. If you found this journey into the invisible matter shaping our universe compelling, please consider leaving a like and subscribing to the channel. Your support helps bring these deep explorations of the cosmos to more curious minds. Until next time, keep looking up at the stars and remember that the visible universe is just on the beginning. The true cosmos extends far beyond what our eyes can see, into realms of dark matter and dark energy, of hypothetical particles and profound mysteries, all waiting to be understood. Sleep well tonight, knowing that you're surrounded by the invisible scaffolding of the universe itself. The axions, if they're real, are keeping you company in the darkness, shaping the very galaxy that gives you a home among the stars.